Well, hi there. We're trying something new. We're uploading this week's lunch gathering to YouTube. We hope that you'll enjoy it this way. If you would like to subscribe, there's a little red subscribe button down below and a little bell thing. And if you click on the bell thing, it will alert you to when new videos will be posted to the BDR Net channel. Let's see how it works. Thanks for listening. Well, I'm really pleased to have Tony Peterle for us from WorldCast, and he's going to talk about the APT MPX and any other acronym he can think of. So you've got screen share ability, and we're turning it all over to you, sir.
All right. So you see my screen?
Yes, sir.
Let me bring up the PowerPoint. This is something that was put together by my colleagues abroad, Hartman Forrester and Kevin Campbell, talking about the pieces that go into the next generation broadcast chain. There are several. So we're going to have a quick overview, and then we're going to hit each one in a little bit more detail. So there are 4 building blocks that we've identified as being part of the next generation broadcast chain. The first is being able to transmit a composite MPX signal. It has huge advantages, obviously, if you're sending the same signal to multiple sites for boosters, translators, single frequency networks, main and backup transmitters at different sites, that sort of thing, because you have one audio processor, one place to create your sonic signature at the studios, and then that identical signal can go out to all of the other stations. So you can save a lot of expense on processing while maintaining very consistent sound across the network. That's a whole lot easier over IP than it is in the analog realm, and we'll talk about that here in a minute. Once you start sending MPX over IP, though, you're immediately set with some bandwidth challenges. A full linear MPX composite signal can cost you, I think, if you're doing the full all the way up to get the subcarriers, SCA authorizations, you're in the range of 5 megabits a second. Even if you're truncating it, if you're doing linear 24-bit or 16-bit, it's 3 or 2 megabits per second. So the idea is to try and reduce that bandwidth without sacrificing the quality of the composite signal, because composite it's the beating heart of an FM analog station. The composite signal is everything that goes on the air, so protecting it is a pretty important thing. We'll touch a little bit on our SureStream technology. This has been around for a long time. As you may or may not know, a packet loss when you're sending a composite signal over IP, a packet loss can be a significantly damaging event because you end up asking your transmitter to pass square waves. If there are sudden slews between one packet and the next in the MPX stream coming in, it can really cause some issues with the modulation, and the transmitter could even cause damage. So protecting against packet loss is an essential thing, plus having a little bit of a backup, maybe a way to smooth those glitches if and when they do happen. And another thing, this is kind of a bonus. We hadn't really put this in our original mission brief for this presentation, but we can talk a little bit about synchronization for SFN, because when you're sending MPX over IP, that's the perfect environment to do a single frequency network and get that precise synchronization in both the RF carriers and the content, the MPX signal. So let's take a look at the MPX signal. This is kind of a typical old school way of getting audio content out to various broadcasting sites. You've got your studios generating the signal, your IP encoder, and then it gets decoded at the transmitter site, and you get processed, you put the RDS encoder into it, and then off to the transmitter. So it's all the audio content and the RBDS signal as well. And there are also some subcarriers, obviously, that go on band above the RDS signal. But in general, for MPX over IP, for bandwidth reasons, those get truncated. So using the composite MPX allows you to get that signal to the sites with very little variation in quality from one site to the next. So you've got exactly what you need. You are reducing the number of redundant devices, because you can have that one audio processor and then send the identical signal to multiple sites over IP. So this can go either MPX over AES, or there are some manufacturers, ourselves included, that have hardware that can accept a composite or an analog BNC connector, coaxial analog composite signal in, and digitize that and send it on across to the transmitter sites, where it can be decoded either as an analog signal coax or as MPX over AES, depending on what your gear at the site needs. The levels of the analog signal can be adjusted very precisely in the digital domain, so you can really control the level of the MPX signal, the level of modulation that gets sent on to the transmitter. And we can do this obviously with AES interfaces on our 1U codec. So whether you've got analog at both ends, analog at one end, or AES everywhere, you can accommodate that, and the technology works regardless. It works the same either way. Sorry, it's been a long time since I've given a presentation. So the composite signal you're all familiar with. So this is a handy little chart that kind of shows us the different modes and the bandwidth. So you can truncate everything above the RDS signal, which gets your bandwidth down quite a bit. So you can see if 24-bit, if you're taking the full composite signal, it is 4,600 kilobits a second, so almost 5 megs. Full signal at 16-bit resolution is just over 3 megs. And then if you truncate it, that gets down to about 3 megabits per second on a 24-bit, and a little over 2 megabits a second on a 16-bit sample. So these are the bandwidths for essentially linear, for direct encoding of the composite signal. And so you can see you can get it down to about 2 kilobits or 2 megabits per second by truncating and by using only a 16-bit algorithm. So that is one way that you can reduce the bandwidth. If you go beyond that, then you need to talk about compression, and we'll discuss that in more detail a little bit. Simplifying the signal chain, you also have to guard against packet loss, because, as I mentioned, if you lose packets and you start getting incomplete information in a composite signal, it can cause some max excursions on the transmitter in terms of modulation. The peak limiter can suppress those. Carrier deviation can rise if the composite MPX signal becomes full level noise, which it can if packets are being lost. The redundant streaming technology is one excellent way to help mitigate or protect against this packet loss. But it also is a good idea to have some sort of an overmodulation cancellation algorithm, some way in the software to catch any of those tremendous slew rates that can cause the square waves and cause the issues with overmodulation, and and take care of that before it causes a problem in your on-air broadcast. And here's a little bit of analysis of what we're talking about. So this is running at 2% packet loss, and you can see if you run 2% packet loss and you don't have some sort of overmodulation cancellation, then you've got some serious overmodulation. You're going beyond your envelope, which is not desirable in any case. So with the overmodulation cancellation at 2% packet loss, you're still well within your envelope, and you've got no issues. Okay, so that was just kind of the general concept of MPX over IP and some things that you have to watch out for. Do we have any questions at this point?
Tony, what about HG?
We'll get there. We can talk about that when we get to the synchronization part.
What is the quality difference between 16-bit and 32?
16-bit and 24-bit. I don't know, how do you measure quality? It can be very subjective. The analysis that we do of the composite signal at the other end, it's difficult to discern a difference between a 16-bit and a 24-bit sample. But maybe we just aren't looking closely enough. There must be some difference, all those extra bits.
So would you lose separation as well as possibly RDS? Or?
No, because the composite signal is being sampled as a whole. So you've got the whole composite, which is essentially an analog signal. And so MPX over IP is sampling that analog signal, which includes the left plus right, left minus right, pilot, RDS. So all that comes in the composite, that gets sampled. What you're losing with the lower bit rate or the lower sample rate is you're losing the precision of that sample. So in cases where the sample, the modulation is varying widely, the composite signal has a wide swing, it's not going to be as smooth a transition. It's not going to match the analog signal as closely as it would with a 24-bit sample.
Tony, Richard Rudman here. What would the configuration look like if you were distributing using KU band satellite? 192 kilobits per second bit rate.
Yeah, that's you're not going to be able to send a composite signal over 192 kilobits a second. I don't believe. You could do audio over that, but I don't. I mean, I don't think there's any solution on the market that's going to get a composite signal down to only what was it, 192 kilobits a second?
Yeah, I was thinking that would be the case. I just wanted to hear you.
Yeah, I mean, if you could crunch a composite signal down that small, I don't think it would come out very well on the other end.
Probably not.
All right, theoretical exercise to try sometime. So let's talk about different ways that you can save bitrate. So we want to reduce the IP bitrate as much as we can while maintaining the quality of the composite signal. So as a composite, as I just mentioned, is sort of an analog signal. It is an analog signal. Broadcasters spend an inordinate amount of money producing that composite signal between the processing and the music library and the talent and the studios, and trying to make sure everything is best, finest quality to make the best composite signal that you can. So once it's created, it's a unique, dynamic, special thing we have to treat with care. So we can roll off everything above 64 kilohertz in the composite. If we don't care about the SCAs, we're just doing the RDS and the stereo. So that gives us some bit level savings, but we need to compress a little bit more because 2 megabits per second is not reliable. 2 megabits per second is not available in as many places as 1 megabit per second. So by compressing the composite signal in its entirety, we can squeeze that bit rate down to 900 kilobits a second without losing any of the quality or the fidelity of the composite. It's what we call a non-deconstructive compression, and we do that. They described it as a quasi-linear approach to compression, but it is packet-based, and so each packet contains all the information for a particular sample. There are some solutions that use a group of packets approach where you send like a keyframe essentially, or a key packet, and then subsequent packets will transmit only the differential data between that packet and the packet that preceded it. And in those cases, those types of algorithms, as in the audio realm, if you lose one packet of what in audio would be called a frame-based algorithm, you lose one packet, then your actual loss of the stream is going to be more significant. You can lose many packets and have a more significant, more noticeable interruption in the audio. Same thing with the composite. If you're doing that sort of follow-on differential-based encoding compression, then loss of one frame is going to invalidate all of the frames that follow until you get to the next keyframe, the next key packet. So that's a couple of important things to keep in mind, because what we're trying to do, the eventual goal is to get the best quality that we can from point A to point B. So our approach was let's treat this composite signal like the entity, the single entity that it is, and compress that single entity so that it comes back out the other end intact. So as we mentioned, lossy links are not a problem anymore with the redundant streaming technology. It works on any content, any bitrate, audio, video, composite, whatever you can send across a network connection. If you've got the bandwidth to do redundant streams, preferably over different providers at each end, you can run the packet loss down to almost nil, even on unmanaged public internets. the example that I generally refer to is we set up a transatlantic audio stream between Belfast and Miami using just the cheapest connections we could find. We had basic business DSL on each end, and then I think I had my Comcast cable on the Miami end for a while, and they were using WISP or something for their other leg in Belfast, and we sent audio across the ocean for almost 6 months without a single lost packet. So the redundant streaming technology is simple, it's very effective, and it's a great way to protect against packet loss. So another aspect, or another way to approach the MPX signal, is to look at it and see within the composite signal the component parts that make up that component, that composite. So essentially you would get the composite signal, and then you would essentially demux it. You would decode it, demodulate it. You would pull out the audio. You can run that through an audio compressor. You can pull out the RDS part of the composite and the pilot, and pass those along. It all gets packetized and sent over the IP transport network, and then at the other end, you have to decode all the packets and then essentially recreate the composite signal. You have to, because you get audio, and then you send it back in and add in the RDS and the stereo pilot, and boom, out comes a composite at the other end. So in this case, there is potential for variations from site to site, because each site is essentially creating its own new composite signal. Albeit with digital data, it should be fairly accurate, but it's just a different approach. This does allow you to get to a little bit lower bandwidth total, but there are some downsides in that you're essentially taking this carefully created composite signal and disassembling it, transporting the pieces individually, and then putting it all back together at the other end. So using composite over IP, you can reduce the amount of your redundant hardware. Cost reductions, you've got one processor that is going to deliver the same sound to all of your transmitters. You can use the MPX, APT MPX to reduce your bandwidth. You can use the SureStream to reduce the packet loss. You can use the overmodulation cancellation to iron out or smooth out any variations that do come through if there are packets that do end up getting lost. All right, so that's the meat of the MPX over IP, and we'll open the floor again for questions, some of which I may not have the answers to.
Why would you do the break down the composite, send it out, and then recreate the composite? Why not just send your audio and your subs and everything at the start and make it in a composite at the far end?
Well, the big advantage to sending MPX over IP is that you can send one signal, essentially one composite signal, to multiple sites, and have it come out more or less the same on each end. So you can, it's the one-to-many concept that's really kind of the big seller for MPX over IP for some broadcasters, right? They're not. I mean, unless you have like a main transmitter at one site and a backup transmitter physically at a different site, well, then you could, have one audio. You could send the audio out to both sites and just have them do their own thing, but it's maybe better to. I don't know. It's a choice. Broadcasters will set it up however they like.
Have you done this over a wireless Ethernet link, like a Ubiquity link, a 5 gig type thing?
Yep. We've done APT MPX over not over satellite, because it's still, it's almost a megabit per second. You can get that kind of satellite bandwidth, but it's not cheap. But yeah, we've done it over cellular, 5G, 4G. We've done it over Wi-Fi. We've done it over microwave, Ubiquity, managed microwaves, and essentially any kind of band, any kind of network that can handle the bandwidth, you should be able to use. Anyone else?
It seems like you could take your encoder and your decoder and build a 5 gig device and literally have a complete composite STL system at low cost, and in a band where you don't, like
Sure.
Ubiquity does.
Yep. We don't play around in the microwave RF field yet. If we see a market, that's a place that maybe we could go. We focus mostly on the FM, and we also have built some DAB and DVB stuff in the past. All right.
Eric Skase has a question here. AES 67 support?
Well, our structure for our codecs is that they can pass any packetized content. So if you got AES 67 coming in packets, then by gosh, we can forward that on with the redundant stream protection, and it'll come out just peachy on the other side. Okay. So now we motor into some bonus content. SynchroStream. This is something that has been deployed in New Zealand, a couple other spots around the world. The feedback that we're getting is very good. We are getting some more demo early hardware here in Miami within the next week or so that we're going to be sending on to a couple of key customers for testing. SynchroStream is the idea of being able to synchronize IP streams, either IP audio or composite MPX streams between multiple sites with a high level of precision. It's a hardware and software option. We make use of the 10 megahertz clock and the 1 PPS GPS signal. It is very, very stable and can compensate automatically for latencies, dynamic latencies, changes that happen in the network, and can adjust the fixed delay at the output of each of the decoders in levels of 125 nanoseconds. That's particularly interesting for single frequency networks, as we'll see here as we we move on. So there's the hardware, the new hardware with the GPS clock inputs, and then we can do the AES digital MPX 192 kilohertz. On our other hardware, we can do it as analog as well. So how this sets up is you provide a constant delay at the decoder. The encoder, when it sends out the stream to all the various receive sites, it is going to set a target latency. So there's going to be a target latency that says, okay, at this time, this is when this packet should be broadcast across the entire network. And that, of course, you're going to set that target latency based on the latency between your various links and the jitter and how much that latency varies over time. But you'll set that target latency to compensate your worst case scenarios. And then at each decoder, you can adjust the individual output by those very fine increments of 192 nanoseconds. So here's the encoder that defines the rough target latency. So in this case, we've defined it as 250 milliseconds. And then the decoder can adjust that as well to set the timing between the transmitters at the different sites. So in terms of a single frequency network, single frequency networks are becoming, they have been in use, of course, around the world for many, many years. They are becoming more of interest in the US as people add boosters to get better signal into overlap areas or places where the main signal from the main transmitter may be shaded. And so single frequency is just what it says. It's multiple transmitters covering an area or a large area that are all broadcasting on the same frequency with the same content. So the idea is you've got to synchronize the carrier of the transmitters, and you also have to synchronize the content and the modulation of the transmitters very precisely in order to minimize interference in these overlap zones where the two signals cover each other. So that's controlled primarily by timing. We've got, we can talk about that here in a little bit as well. So you set up your single frequency network, you put your transmitters up, you have the coverage and area. Sometimes terrain helps a lot in reducing. The idea is to if there is interference between two of the transmitters, you want that interference to be happening in a place where people are not, right? So you want to be able to steer that interference, that mush zone, away from, your highways and your highly populated areas, and get it over a river or, something like that. So you've got to control not only the position of these mush zones, but the size of the mush zones as well. That's all about the synchronizations, how tightly you can synchronize that composite signal, that modulation between the different transmitters. So to synchronize, you use the GPS, of course, the carrier synchronization. That's fairly simple, but getting the content synchronized and the level of content, level of the composite MPX signal is also important, because different transmitters will react slightly differently to the composite MPX signal that's coming in. So if it's all digital, that's much easier. So a typical SFN transmitter site, you've got the GPS receiver that's locking into your locking the transmitter to lock the carrier frequencies. So the frequencies are synchronized, the actual carriers are synchronized, and then your GPS, one PPS and the 10 megahertz go into the receiver to synchronize the composite as it comes out of the decoder. So the overlap area, the receiver is going to get both RF signal constantly. They'll get them both. So for an illustration, if you change the delay, so in terms of the overlap zone, if you change the delay by a microsecond, that is going to move the overlap zone by about 300 meters in the real world. And that will be, depending on whether you're adding or removing a microsecond of delay, that's going to move that interference zone to or away from that transmitter that you're adjusting. So if your smallest increment of adjustment is only a microsecond, then you can only move that zero delay, the perfect zone, right? Where the reception is going to be perfectly synchronized between the two transmitters. If you're moving in 1 microsecond steps, then that zero delay zone, that perfect synchronization zone, is going to move 300 meters at a time, either way. So if you can adjust that with a smaller increment, right, and move that interference zone or the perfect reception zone by 10 meters or 30 meters, that's going to be a big help in getting your SFN set up and working the way that you want. So in the real world, this last line is the good one. Interference results mostly from timing mismatches of the FM modulation. Like I said, synchronizing carriers, that's not too hard, but the timing of the modulation is really critical. So here's an illustration that shows that perfect reception zone, the equal delay line in between the main transmitter and the booster signal there coming on the right. So that's the best possible reception between those two transmitters. And the more finely you can adjust the latency between those two transmitters, the modulation latency, the more finely you can adjust that equal delay line. So you get smaller areas of interference, and you get very precise adjustment of where the perfect synchronization zone is going to be with those very small increments. So you can see it's 37 meters. If you're adjusting with increments of 125 nanoseconds, 37 meters is how much that equal delay, that perfect reception line is going to move. So again, with your GPS locked transmitters and your GPS locked MPX encoders and decoders, you have an excellent chance of deploying a single frequency network with a high degree of success. All right, so probably a few questions on SFN.
Well, Tony, on that whole thing that you just went over, was that, and your conclusions, are they based on reception of analog FM?
Yes.
Okay.
So we are talking now about multi-frequency networks. And so here we can talk about using that synchro stream to not only synchronize the composite between sites, but also synchronize the composite to an HD stream, like an E2X stream that would come out of your audio processor at the studio. because it's the same way, whether you're synchronizing the same content between two sites or you're syncing two feeds of content to a single site. This is an area that we're going to explore. Our test bed customer is eager to explore this as well, because after HD was just coming on when I joined the company in 2005. So we're now 16 years and counting into it, and people are still fighting the sync between the HD and the analog. So we are eager to get our hardware into the testers' hands, which I said should happen within the next couple of weeks, and we can find out if it can do what we think it can do for HD. No reason it shouldn't be able to do it, but until we have it up and running and actually, proving with the pudding, we're going to kind of withhold our trumpets for the time being. But it's the same concept as a multi-frequency network. So you've got the same program on different frequencies. This is very common in Europe, where the RDS alternate frequency table will actually retune the radios as they drive from one coverage area to the next. The RDS will detect which frequency has the same program on it and switch. And if you've got your audio synchronized, then it's inaudible. The listener doesn't even know that their radio has changed frequencies. So that's a much lower level of precision than is needed for SFN. So if you can do synchronization that is suitable for SFN, then multi-frequency networks are already done. It's easy. So this is a typical multi-frequency network. So again, you've got your program coming out. You can send it to multiple different transmitters on different frequencies, nicely synchronize the audio with the NTP server, and you get good precision on the audio, so that when the tuners or receivers tune from one frequency to the other, there's no audible hesitation or glitch or anything in the audio. Another slide on content time alignment. The same thing. You've got your target latency value, and then you've got a trim value that you can add or subtract. Little detail on the NTP timestamping that we can use for the multi-frequency network synchronization, and a couple of the setup screens. So you've got your managed link latency and your target latency settings, and then the fine adjust on the far end. You can trim that target latency a little bit to make the best match. So again, just a quick review. The next generation broadcast chain, you've got the advantages of sending composite over IP. So you get consistency between sites. You can easily distribute the same composite signal to multiple sites. You've got different ways to compress that composite signal to reduce the network bandwidth that you need. The APT MPX is what we call a non-deconstructive, that treats the composite signal like it's holistic thing that it is. You've got to protect against packet loss. You've got to protect against any packet loss that does occur, right, with the overmodulation cancellation. And then if your project, your network requires, then you've got the option to do the synchronization, either to a low level of precision for multi-frequency deployments, or to a very high level of precision for SFN type networks. So the idea is to keep things simple. You've got less equipment at the site. All of your stations sound the same. You've got nice digital alignment, less cost. The quality of the signal is maintained. The composite signal is protected, and you've got what you need with a minimum cost and minimum hassle. That's the goal. Trying to make life easier.
Are you guys doing this in Europe, in particular Italy? We were in Italy, was it 2 summers ago, and I drove literally from one end of Italy to the other, and I listened to the same classic rock station,
yep,
at least the same format, and
yep,
it was unbelievably seamless. I mean,
yep,
I'd have to look down at the radio occasionally to see what frequency it was on, but using RDS and that it was perfect.
Up until last year, I visited the factory in France probably once or twice a year for training and project development and whatnot. And I have not seen a radio in a French car that has a frequency display on the face of it. All they show is the program service name, the eight character name of the program. I'm sure there's a menu somewhere that you can punch through and see what frequency you're tuned to at any given time. But yeah, it's like you described. You tune in a program in Bordeaux and you drive to Paris and you are still listening to the same program. It's seamless, but along the way, your tuner has changed frequencies 20 times.
Yeah, it's really cool.
It's very neat technology.
On your MPX, the composite version. So if I were to move my audio processor from my studio to my from my transmitter site to my studio, how accurate is the audio going to be going into my transmitter as compared to the input, as far as any sort of overshoots, artifacts, level differences, etc.?
If are you doing MPX over MPX over AES, or are you doing analog MPX with the coax?
It would be analog MPX, and then running HD with a synchronizing device to keep them linked.
Keep them linked. Yeah. Well, there's always going to be some vagaries in the network, but provided that provided you've got good network connectivity, there will be no observable difference between the composite signal that comes out at the other end, because even if it's analog going into the codec, it gets digitized right then and there into the AES 192 sample rate. So that once it's digital, it's going to be exactly the same coming out the other end. We just decode that digital signal and bada boom.
But as far as levels go and everything should be maintained.
Should be identical.
But if to go back to your original comment, that as long as the network is solid, right. What would be the worst case scenario? Is, let's say I'm running over a public internet connection, or I'm running over a even a point-to-point ubiquity link or whatever, and I have a snow fade, and all of a sudden I'm dropping some packets.
Sure. Well, we had that one slide that showed the 2% packet loss, and you could see that there was some overshoot, and that's typically what happens when you have packet loss on a digital composite signal coming into a transmitter. Is you're going to get some overshoot, and so you can cancel that with a peak limiter at the site. That's not the best way. The best way is to prevent the packet loss in the first place as much as you can by having multiple streams going across divergent paths, and then to have some sort of an algorithm in the decoder end that will detect any overshoots in the composite signal that do come through and take care of them before they get to the transmitter. So you don't have to use that peak limiter for that purpose.
So in other words, it glitches.
Sorry?
It glitches if it drops too many packets.
If it drops too many packets, yeah.
Okay.
Yeah, and so that's you protect against the packet loss, and then you have some sort of software in place to mitigate the effects if packet loss does make it through.
Gotcha. Okay, thank you.
Sure.
How much is the multiplex composite encoder and decoder?
Gosh, I don't know. This is not a sales presentation.
Oh. Never mind.
I wasn't prepared to answer that question. I know the codec themselves is I think they're around 2,200 for the codecs, and I don't think it's much to get the MPX option is in there. The synchro stream part is going to be a little bit more expensive because that's got extra hardware with the GPS receiver.
That 2,200 for both ends?
No, it's per end.
Okay.
And that's for the 1U, one box stereo duplex. One size doesn't quite fit all, but fits most.
All right. Well, we have quite a few questions, and I hope that your server's back up. Do you want to have a slide here with your email address on it, Tony?
No, because I didn't write this presentation. So we've got worldcastsystems.com. So I don't know, Barry. I'm t.peterle at worldcastsystems.com.
Right.
So let me. There it is.
There you go.
I'll leave that up there.
And we'll hope that your server is back online post-toasty.
Yeah, absolutely.
All right. Well, I sure want to thank you on behalf of, we had 50 people that had signed in while you were talking.
Oh, that's great.
Glad to have had you today. We'll hope you'll come back to us another time with more of the WorldCast products.
Yeah, actually, we the next one we're probably going to talk about is our Smart FM technology, which is a software that we developed that can reduce the operating power costs of an FM transmitter by up to 40%.
Interesting. Indeed.
Yes.
All right. Well, again, I want to thank you. You don't have to go away. We'll
Nope.
so sit here and talk for a while.
Sure, I'm happy to answer any. If nobody has any questions about what we talked about today, it could be about anything else WorldCast does or has done.
There you go.